Hello everyone. Today we're going to talk about a bunch of NP-complete computational problems you might come across. So first, let's have a quick recap for what NP-complete is. So in order to know that, you need to know what card production is. So if you have two problems like, let's say, Sudoku solving and graph coloring, we say Sudoku solving card reduces to graph coloring. That means and that kind of means, like, intuitively you could think of it, it's not harder than. It's not harder than. Alright, so what does it mean more specifically? It means we can take an instance of Sudoku solving. For example, let's have this Sudoku puzzle here. So let's call this X our Sudoku puzzle. So we already have partially filled in clues like this. But yeah, we want to say it's not harder than graph coloring. So what's graph coloring? Graph coloring is when you have a graph like this, so you have nodes and edges. Let's say you have this graph and you want to assign it different colors so that no two adjacent nodes have the same color. So if you give this node color 1 and you can't give this node color 1 as well because there's an edge between them, so you have to give this node color 2, for example, right? And the idea is card production means we can transform an instance of one problem into an instance of another one. But there have to be special properties with that transformation, right? Which we'll go into in a moment. So yeah, what the idea of the transformation is, you want to map one instance into other so that solving this one gives you a solution for this one. So what does that mean in an example for graph coloring? Well, Sudokus, you can just look at it as a graph coloring problem because you're filling up digits and there can't be like a conflict within a row, column, or a box. So for example, in this box, that means in terms of graph coloring, if your colors, they're the digits from your Sudoku, that means you can have here you have the complete graph for this box, for example. So all the edges are filled in basically, so none of these can have the same color. And then you can do the same for your row, right? So you connect up all the edges in a row, so nothing in this row can have the same color. For example, this has 3 and 4 from this, right? And then you can do the same with columns. So in your column here, I guess you can draw another box here. And in the column node 2, yeah, you draw edges between each pair of nodes as well, because that means they can't have the same color, and so on, right? You can kind of complete the picture. But the idea is it solves it in a way that, so yeah, there's two things this transformation has to satisfy in order for it to be a card production. One is that if X is a solution for Sudoku, so X in Sudoku means the output would be yes. So X is a solution to Sudoku if and only if g of x is a solution to the graph coloring problem. So this is kind of slightly a variant. It's like partial graph coloring because you already have some colors filled in just to make it match with Sudoku. But you can show it's equivalent to the regular coloring as well. So the idea is x is a yes. If x is a yes for the Sudoku is solvable, then g of x is a yes. Then g of x is a yes for the graph coloring problem, and conversely, if x is a no, then g of x also has to be a no. So it kind of this mapping, this transformation from one input to another input has to preserve correctness and incorrectness, like truth and falsity, like what are the same properties. And then the second property is that the function g can be computed in polynomial time. So that means it's just really efficient to compute the function, so you can move from one problem to the other really efficiently. So what does this mean in practice? Imagine you need to write a Sudoku solver, but you don't have an algorithm for it, but you know you have an algorithm for a solver that tells you whether a graph is colorable or not. So you have like a solver for the coloring problem. So what you can do is, well, you can just take a Sudoku, transform it into a graph, and then run your coloring program on that. So using this transformation, you can do that. That means the Sudoku is not much harder than the coloring problem, because you only need to do this work of transforming it into a graph, this work of g of x, which is polynomial time, so it doesn't take much time. You only have to do that kind of work to get to Sudoku to get a Sudoku solver if you have a coloring solver. That's the idea. So how does this then connect to NP hard? Well, if a problem is NP hard, let's say coloring, for example, is NP hard. If you can find a carp reduction from every problem in NP to it. So we can visualize it like this. Let's say this is NP, and the dots there, every problem in NP, and we can find a carp reduction from every problem to it, right? So it's kind of saying everything in NP is not harder than the coloring problem. So that's what it means for problem to be NP complete. So I guess you could say that means that call is NP hard, sorry. Yeah, that's the definition of NP hard, if we can carp reduce everything in NP to it. So it's kind of the hardest problems that are harder than everything in NP. And what does NP complete mean then? NP complete is just if it's NP hard and in NP. So it's the problems within NP that are the hardest. So if we visualize this, if you remember here we have, say here we have NP, then here in the easiest edge of NP we have the problems in P, and then we have the NP hard problems here. So that's where everything in NP can carp reduce to it. And then here in this intersection, that's where we have the NP complete problems. That's the idea here. So now that you know what an NP complete problem is, now that you've been reminded, I can give you a list of NP complete problems. So first of all, let's look at independent set. So that's one related to graphs, related to graph theory. So your input for an independent set is going to be a graph G and an integer K. And then the output's going to be, so this is a decision problem, so the output's going to be either yes or no. So when is it yes, when is it no? It's yes if G has an independent set of size K and no otherwise. So what's an independent set? So if we take this graph as an example, it has 4 nodes or 4 vertices, A, B, C, D. An independent set is a set of nodes that are not connected to each other, so that are not neighbors. For example, if you take A, C, that's a set of nodes, node A and node C. There's no edge between A and C, so this is an independent set. And then just a set A, just a node A, that's also an independent set because there's no edge from A to A. So that's an independent set. And then the empty set, so that's set containing no nodes. That's also an independent set because there are no edges between no nodes, right? So the kind of idea is statement is that for all So if we look at the actual statement, we say S is an independent set. So as a definition of independent set, if for all nodes uv in S, we have that uv is not an edge, right? So there's no edge between any pair of nodes in the set. So this is then, if S is the empty set, then this is a for all statement over the empty set. So you're quantifying over everything in the empty set. So you're quantifying over nothing, and that just makes it true, right? So you're just saying, this is a condition that has to be true for all whatevers, for all pairs of nodes. But if there are no pairs of nodes, then the condition is just trivially satisfied, right? That's how we do it by default. And then if you look at a counterexample, if we say A, B, C, D, so that's not a set of nodes, but between A and B, there's an edge, this one right here, right? So this is not an independent set. So yeah, that's what independent set is. So let's move on to the next one. That's going to be satisfiability. Also known as SAT. That's a very common one because you're expressing the problems about logical formulas, and you can reduce lots of other decision problems to it because you can express lots of problems as using these formulas. Formulas are quite powerful in that sense. So the input is gonna be a propositional formula. Phi in CNF, so conjunctive normal form. So what does that mean? It's, for example, phi would look something like x1 or x2, and not x3 or x1 and x3. So x1, x2, x3, that's what we call truth variables. So they can either be true or false, and you connect them with or statements, and statements, not statements, and then the whole, depending on whether you assign true, which truth assignment you did to the variables, which variable assignment you did, the formula will either evaluate to true or false, right? And CNF just means you have, this is what we call a clause. It's a bunch of or statements, right? It's this or this or this or this, and you connect them with and. So that's what it means to be in CNF. And then these things, they're called literals. So that's either propositional variable x1 or it's propositional variable not x3, for example, right? So either a variable or not a variable. And then, yeah. So what's the output of satisfiability gonna be? So the output is gonna be yes if phi is satisfiable, and it's going to be no otherwise. So what does it mean for phi to be satisfiable? It's satisfiable if we can find a variable assignment that makes the formula true, basically. So this example, this formula phi, this is satisfiable. And why is this one satisfiable? It's satisfiable because we have an assignment. So with the assignment, x1 becomes true and x3 becomes true, for example. With that assignment, well, this clause is true, right? x3 is true, then x1 is true, which makes this clause true, and x1 is true, which makes this clause true. So every clause is true. So that assignment satisfies the formula phi. So that's satisfiable. Then an example of the formula that's not satisfiable would be x1 and not x1. That's not satisfiable. And this is much harder to find out because, yeah, you kind of need to make sure that no matter which truth assignment you pick, it's not gonna be satisfiable. So so yeah, so that's why it's an NP hard problem. It's because, well, figuring out which formulas are not satisfiable is really hard, basically. And then you have a variant of that called free set, and what that just means is that, so the input and output are the same. It's only more restrictive in that clauses have at most 3 literals. So that means you can't have, for example, x1 or not x1 or x2 or x3. You can't have that as a clause, right? That's not allowed because it has 4 literals, 1, 2, 3, 4. So you're just limiting, yeah. And in actual fact, every formula can be expressed as a free set formula. So yeah, that's why this is still an interesting problem, because yeah, we can still answer the satisfiability question for any formula with it. Great, yeah, so then let's move on to the next one. So it's kind of one I mentioned before. It's called K-coloring. Or yeah, graph coloring specifically, so K-col for short. So the input is going to be a graph G and an integer K. And the output is going to be yes if G is K colorable. And it's going to be no otherwise. So what does it mean for a graph to be K colorable? Well, it just means we can color it with 4 colors. So for example, if we have this graph, the classic, so yeah, what we can do is we assign color 1 to this node, and then in graph coloring, the idea is both nodes that are adjacent to this can't have the same color, so we can't use 1 here. So let's use 2 here. Then we go to this node. This one can't have 2 because it's adjacent to this one, so let's give it color 3. And then this one can't have 1 and 3, but we can give it color 2, right? So we found a free coloring. That means we found coloring that uses 3 colors. So that means this graph is free colorable, right? But we might find a more efficient coloring as well. For example, in this case, in the same example, if the thing is with this 3, that one's only adjacent to 2s, right? So we can just make this 3 be color 1. So that would look something like this, right? So now we've only used 2 colors and we found a coloring. So that means the graph is 2 colorable. So to recap, the K-coloring problem looks at graph G and tests, and it answers the question of whether you can color it using K colors. That's the idea, right? Cool, then let's move on to the next one. So the next one's going to be vertex cover. Or VC for short. So again, as an input, you have a graph G and an integer K. Then as your output, you're going to have yes if G has a vertex cover of size K and no otherwise, right? So what's a vertex cover? That's so if we look at our recurring example for graph problems here, so we have nodes A, B, C, D, and then these are the edges. So then the vertex cover is a set of nodes that are not adjacent. So for example, is that right? No, sorry, yeah, it's a set of nodes that are adjacent to all edges. So AC, that is a vertex cover, because each edge, like these two edges, so yeah, this edge and this edge, they're adjacent to A, and this edge and this edge, they're adjacent to C. So maybe let's backtrack a bit. So how do we represent a graph? Graph G is a pair, the set of vertices and set of edges. So in this case, set of vertices would be A, B, C, D, right? Those are the nodes of the graph. And then the set of edges would be, well, you take pairs of nodes and put them in a set. So we have an edge from A to B, so AB is an edge, and then BC is an edge, and then CD is an edge, and also AD is an edge. Right? So yeah, that's how we define a graph. So that's the notation we use. So yeah, a vertex cover, a set S is a vertex cover if for all edges UV in E, we have that either U is a member of S, so is in a vertex cover, or V is in a vertex cover. So each edge needs to have a representative in the vertex cover, in the set of nodes there. So then, for example, AB, this is not going to be a vertex cover because the edge CD doesn't have a representative in there. Like neither C nor D is in the vertex cover here, right? Cool, that's the vertex cover problem. So let's move on to the next one. Let's call it interval selection. The interval selection problem. ISP. It says an input. This takes a set of real intervals, so intervals of the real numbers. Let's call this set I. Then as an example we can have, for example, we have 1, 2, we have the interval 1.64, and we have the interval, let's say, pi square root of 17, right? Those are 3 real intervals, and might be useful to draw out, well, what do they look like? Because we're going to care about whether they overlap or not, right? So let's draw them out like this. Let's give them names as well. This is going to be F, this is going to be G, this is going to be H, and they're going to correspond to F, G, and H here. So this goes from 1 to 2, this goes from 1.6 to 4, and this goes from pi to the square root of 17, right? And then what's the problem going to be? What are we going to do with these intervals? Well, we're going to look for the... so yeah, this is a bit different. We're no longer doing optimization problems, yes or no. We're no longer doing decision problems, yes or no question. Now we're doing optimization problems. So we're trying to find the best of something, like the maximum or the minimum or the whatever. So in this case, we want to find the largest subset S of the intervals, so the largest subset of intervals that don't overlap. And what does it mean to not overlap? That means for all fg in S, we have that the intersection between f and g has to be empty, right? So why do we do this? This is useful for scheduling. Like if you have to schedule lots of lectures or something during a day, you have to pick which ones are not going to overlap. Which ones can you schedule in the same room, basically. You're selecting all the ones that you can schedule in the same room without having a conflict, right? So if we look at examples, if we select f and g, those intervals, so that's not a valid solution to the interval selection problem, because f and g overlap at 1.7, for example. But then fh, for example, that's a valid solution because they don't overlap. And it's also the largest subset. For example, you could say just f, it doesn't overlap either, but that's not going to be a valid output because it's not the largest subset. This subset is larger, right? And this one is in fact going to be the largest because any larger one will need to include g, and that just overlaps with everything else. There's no way to include that, right? That's the idea of interval selection. So then let's look at the next problem. We call this linear programming. Linear programming. So this one's going to have an interesting relationship. So the way I'll write it down, it's not going to be, it's going to be in P to be specific. It's not NP complete, but there's a slight variation of it, which is NP complete. So that's why we're talking about this. But the one in the variation in P is useful as well. So it's also an optimization problem. So for the input, you have an objective function. So the objective function is just the object you want to minimize or maximize or optimize in some way. So for example, let's take f of x1, x2 is equal to x1 plus x2. So yeah, why do we call this linear program? Because all the function here will be linear. That means when we have a variables x1 and x2, they can't be multiplied with each other. You can't use powers of them, right? But you can multiply them with constants, add constants at the end. You could say plus 4 here, but it doesn't. That won't make a difference for minimizing or maximizing, really. So the objective function is going to be some linear function. That's going to be the aim to maximize or minimize. But that's not quite powerful enough. We want these variables to have some constraints on them, right? So what are these constraints going to be? For example, constraints could be minus 2 x1 plus 8 x2 is bigger than 50. 5 x1 plus 2 x2 is going to be at least 100. And x1, x2 is going to be at least 0. They're going to be positive, right? Or non-negative. So the idea is here you still have linear functions and they're going to be bigger than some constant in every case. So these are the constraints that you have to follow. So yeah, x1, x2 have to follow these constraints, but still be minimized. That's the idea. So this has lots of application in economy because there usually you want to look at demand, supply, that sort of stuff. So this can be very useful. So yeah, what's the output then? So the output is a solution. For example, x1 equals to a, x2 equals to b. That does two things. Either so let's say it minimizes the objective function. F, right? So it minimizes this function subject to the constraints. So it respects the constraints too. So it's a solution to the system of inequalities such that the function is minimized. So there's slight variance to this as well. For example, you couldn't just flip the greater than sign to a less than sign, or greater than equal to less than or equal sign, or so swap it out for the strictly signs. Or you could, instead of minimizing the objective function, you could maximize the objective function if you wanted to. Like if that function is your profits, you would want to maximize it, right? But then, so this problem is in P, so this is really efficient to solve. But there's another variant, ILP, integer linear program, that's exactly the same, except the solution has to be integers, right? Integers. So more specifically, A and B have to be in Z in our little example here, right? This variant is going to be in NP, because it's going to be much harder to find integer solutions. Like with real numbers, you can just go take all the decimal values in between. That gives you a much bigger solution space. It gives you much more room to work with. But this is actually going to be really hard to do. It's going to be in NP, because you have to guess much larger numbers. So it might take potentially a really long time. Yeah, so that's the idea. So why is this useful? It's also similar to like with satisfiability. We can express lots of optimization problems this time in terms of linear programming. So as soon as we can express a problem using a set of inequalities like this, and we can have whatever cost we want to optimize, cost we want to minimize, or reward we want to maximize, whatever. That's what linear programming is going to be for. So it's like a really versatile tool in that regard. Great. So now let's have a look at the party problem. So the party problem, it's not a political statement, but it's still a computational problem. So what's the input going to be? The input is going to be a tree. So it has two inputs. First of all, it has a tree. So tree is just a special kind of graph. So we're going to say VE. So what does it mean to be tree? It means a graph with a root and no cycles. For example, this graph here. This graph here is a tree. It has this, we designate it as the root, right? And it has no cycles. For example, this would be a cycle, because you can see if you just cross the edges, you can just keep going forever in the same direction here. That's kind of the idea. Yeah, I get you get what a cycle is. You can have like a closed path of edges. So we have a tree and we have a score function. So a score function S from the nodes to integers. So this assigns a value to each node. For example, here the root will give it value 3, we'll give this value 6, value 5, value 4, value 4, value 6. And then what's the problem gonna be? What's the party problem? Well, the idea is, you imagine the nodes are different people you want to invite to a party, but they all work in the same company. And if there's an edge, that means one is the boss of the other. So this node is the boss of this node, this boss is the boss of this node, and so on. And you don't want to invite people to the party that have a boss relationship, right? So if you invite this one with value 5, you don't want to invite this one with value 3 as well, because it's the boss of the former. But then also you want to prioritize inviting some people over others. For example, it's much more important that this one is invited with a value of 6 than this one with a value of 4. So that's what the values mean, right? So how do we express this a little more formally? Well, we're going to say the output is going to be a subset of nodes, so S subset of V, that maximizes. So we want to invite as many people as possible, so we're going to maximizing in. Well, not necessarily as many people as possible. I want to maximize the total score. So we want to maximize what value we get out of it, right? So that maximizes the total score. What's the total score? That's going to be the sum of the values. So the value function is S of V. So it's the sum over the V's in capital S, right? In your subset. But then we have the constraint such that so no nodes in S are adjacent, right? Kind of like an independent set. So for all UV in S, we have that UV is not an edge, right? Yeah, that's the idea of this problem. And yeah, this problem, you can express it as a linear program, for example. You can think about how to do it. Can you, maybe? I don't know. Well, something you can think about if you want to. All right, cool. So let's have a look at the matching problem. So what's the matching gonna be? It's pretty simple, it's not a graph problem. So the input's gonna have a graph G, and as an output, it will have the largest, so it's an optimization problem again, matching of G. So what's the matching? Matching M is a set of edges that are non-adjacent. So for example, if you take these two edges, they're non-adjacent. So this is a matching. But then these edges, they're adjacent because they share a node here. So this is not a matching, right? So how do we express that more formally? So for all pairs of edges in our matching, so A, B, C, D in M, we have that they don't share nodes. So AB intersected with CD has to be the empty set. So there's no node sharing going on. They're not adjacent the edges, right? Cool. Almost there, 3 more problems to go. So let's look at the traveling salesman problem. This one is a classic NP-complete problem. This is useful for pathfinding in maps, like route recommendations, that kind of stuff. So as an input, a map, you're going to represent it as a graph. So you're going to have a graph G as well as a cost function for edges. So what does that mean? It means we have this function C, which takes its inputs, edges, and E, and gives you integer outputs. So that's going to be the cost it takes to take each edge, to take that path. And then what's the output going to be? It's going to be a tour of G that minimizes cost. So what's the tour? Let's illustrate it using something similar to our favorite example. So if you have this kind of graph, then each edge has a cost, right? This has cost 3, 4, 3, 2, 5. This one's gonna have cost 1, and this one's also gonna have cost 1. So a tour is gonna be a cycle of edges that visit all the nodes. For example, if you select this edge, then this edge, then this edge, and then this edge, that's going to be a tour, right? So yeah, it goes from one to the other. And you want to kind of minimize the cost, so you sum together what's the cost going to be. It's going to be 3 plus 2 plus 1 plus 1. That's going to be the minimal cost possible, because I don't want to take the 5 or the 4 or the 5. So kind of trying to visit all the nodes. It's like visiting all the cities, and you want to take the path that takes the least amount of time, for example. You want to take the most efficient path between them, so you do that, like checking the cost function, right? Then let's have a look at the knapsack problem. So that as an input has n items. Let's say we have, in our example, we have an item 1 here, we have an item 2 here, and we have an item 3 here. That's one thing it has. Then it has integer weights, w1 up to wn, and they have to be positive. For example, let's say the weight of object 1 is going to be 2 kilograms, the weight of object 2 is going to be 10 kilograms, and the weight of object 3 is going to be 4 kilograms. And then we also have integer values. So what's going to be the value of each of these objects? v1 up to vn, it's all positive. For example, let's say this one has a value of 2 pounds, this one has a value of 1 pound, and this one has a value of 8 pounds, right? And finally, you also have a knapsack capacity. Knapsack capacity C, which is positive. So you have a knapsack like this one. That's your knapsack. And you basically want to fit in items, but it has a maximum capacity of 20 kilos. So you can't pack more than 20 kilos in your knapsack. So the idea with this problem is you want to pack as much value as you can while still being within the capacity. So the output is going to be a set of items that first of all maximizes total value. So it's going to maximize the sum over all the i's in, sorry, so the set S of items that, so yeah, this is going to be the sum of all the items in S of VI, but also they have to fit in the knapsack. What does that mean? It means that the sum over all the items of the weights has to be less than a total capacity. So you can't pack more items than your knapsack can carry. That's the idea here. And yeah, this you can again express as a linear program, kind of. You can try and figure out how. Might be fun. Cool. And then let's have a look at minimum set cover. So minimum set cover. What does that look like? As an input, you have your universe of elements. So it's going to be universe U. Let's say that's going to be 1, 2, 3, 4, 5. So here we've used numbers, but they don't have to be numbers. They can be whatever you want to. It's just some elements in a set. And then you have a list of subsets. For example, S1 is 1, 3, 5. That's a subset. S2 equals 3, 4. S3 equals 4, 5. And S4 equals 1, 2, 3, 4, right? So yeah, so what are we doing with this universe and these sets? So the output is going to be, so it's minimum set cover, so we're minimizing something. It's going to be the smallest collection of sets. Sets that, let's say, let's give an example of a collection of sets. For example, S3 and S4, there's a collection of sets. So you're picking S3 and S4 out of this list of subsets. So a collection of subsets from the list, right? So let's pick S3 and S4, such that, well, they cover the entire universe. So the union S3 union S4 is going to be U, right? In this case, you get 1, 2, 3, 4 from S4, and then you get the 5 from S3. So you get all of 1, 2, 3, 5 from here, right? So you're kind of trying to find out which ones do that. Then, for example, if you do S1, S2, that's not a valid output of minimum set cover because they don't cover the whole universe. And then S1, S2, S3 is also not a valid output because even though they cover the whole universe, there's a smaller one, right, with just 2 sets instead. Great. That's the final computational problem we're looking at today. Hopefully that gives you an overview of the different computational problems you might face. Thank you very much for listening.